Right now, as you sit there listening to me, you are dying. And I don't mean that in some vague philosophical sense. I mean it in the most precise, physical, measurable way that physics allows. There is a quantity, a number, that the universe is keeping track of, and that number is ticking upward inside your body this very second. It was lower when you woke up this morning than it is now. It will be higher tonight than it is at this moment. And when that number gets high enough, well, that's the end of the story. That number is called entropy. And by the end of this lecture, you will understand what entropy really is, why it increases, and what it means for you, for me, for this room, for the earth, and for the entire universe. You'll understand why time moves forward and not backward. You'll understand why you can't unscramble an egg. And you'll understand the cold, beautiful, terrifying logic behind the fact that everything falls apart. Now, let me start with something simple, something you've all seen 1,000 times. You take a cup of hot coffee, you set it on the table. What happens? It cools down, the coffee gets colder, the air around it gets a little warmer, and eventually they're the same temperature. Everybody knows this. But let me ask you something. Have you ever seen a cup of cold coffee sitting on the table suddenly get hot? Has the air ever given its heat back to the coffee and made it boil? No, never. Not once in the history of the universe has anyone observed this happening spontaneously. And here's the strange thing. If you look at the individual molecules, there's nothing in the laws of physics that forbids it. The laws of motion, whether Newton's laws or the equations of quantum mechanics, work just as well backwards as forwards. If I showed you a movie of two billiard balls colliding, you couldn't tell whether I was running it forward or backward. The collision looks perfectly legal either way. So why does the coffee cool? Why doesn't it heat up? Why does the arrow of time point in one direction? This is the mystery, and entropy is the answer. But we have to be careful here, very careful, because entropy is one of the most misunderstood ideas in all of physics. People throw around the word disorder as if entropy just means messiness. They say things like, my teenager's room has high entropy. And while there's a grain of truth in that analogy, it misses the heart of what entropy really is. So let's build this up from scratch. Let's do it right. Imagine I have a box, a simple box. And inside the box, I have a gas, just air, let's say. Billions and billions of molecules bouncing around, colliding with each other, hitting the walls, zooming this way and that. Now, here's a question. How do I describe the state of this gas? Well, there are two ways. The first way is what we call the macroscopic description. This is the big picture. I measure the pressure, I measure the temperature, I measure the volume. These are things I can observe with instruments. These are the things that matter for practical purposes. If I want to know whether this box of gas will push a piston or inflate a balloon, I just need to know these macroscopic quantities. But there's another description, a much more detailed description, the microscopic description. In this view, I don't just know the pressure and temperature. I know exactly where every single molecule is and exactly how fast it's moving in exactly which direction. I know the position and velocity of every one of those billions of particles. Now, here's the key insight. Here's where Boltzmann comes in. Ludwig Boltzmann, brilliant man, tragic story, figured this out in the 1870s. He realized that many, many different microscopic arrangements can give you the same macroscopic state. Think about that. I can have the gas at a certain pressure and temperature, and there are astronomically many different ways the molecules could be arranged to produce that same pressure and temperature. The molecules could be here or there, moving fast in this direction or that direction. As long as the averages work out, I get the same macroscopic readings. Each of these specific arrangements, each complete specification of where every molecule is and how it's moving, is called a microstate. And the macroscopic condition, the pressure and temperature we actually observe, that's the macrostate. Now, Boltzmann asked a beautiful question. How many microstates correspond to a given macrostate? And here's where entropy comes in. Entropy is just a measure of that number. More precisely, entropy is proportional to the logarithm of the number of microstates. We write it as S equals K times the natural log of W. The K is Boltzmann's constant, a tiny number that connects our everyday measurements to the atomic world, and W is the number of microstates. So when we say a system has high entropy, we're saying there are many, many ways to arrange its parts while keeping the overall appearance the same. When we say it has low entropy, we're saying the parts must be arranged in a very specific way. Now let me show you why this matters, why this simple counting argument leads to everything we observe about the arrow of time. Suppose I have a box divided in half by a partition. On the left side, I put gas. On the right side, nothing, a vacuum. Now I remove the partition. What happens? The gas spreads out, it fills the whole box. We've all seen this. Perfume diffuses through a room. Smoke spreads out from a cigarette. This is utterly commonplace. But wait, think about the microstates. When all the gas was crammed into the left half, there were only so many places the molecules could be. The number of microstates was relatively small. But once the partition is removed, the molecules can be anywhere in the whole box. The number of microstates is enormously larger. How much larger? Well, for each molecule, the available volume has doubled. If I have n molecules, the number of microstates is increased by a factor of 2 to the power n. And n might be something like 10 to the 23rd power. 2 raised to the power of 10 to the 23rd. That's a number so large that no words can describe it. So what's the probability that all the molecules would spontaneously go back to the left half? It's 1 over that number. It might as well be 0. Not 0 in principle, mind you. The laws of physics allow it. But the probability is so fantastically, incomprehensibly small that if you waited the entire age of the universe, you would never see it happen. Not even close. This is the second law of thermodynamics. Entropy tends to increase. And now you see, it's not really a law in the usual sense. It's a statistical fact, a consequence of counting. Systems move from states with fewer microstates to states with more microstates because there are more ways to be in those states. It's just probabilities. Let me say that again, because it's important. The second law of thermodynamics is not a mysterious force pushing the universe toward chaos. It's just mathematics. It's just the fact that there are overwhelmingly more ways for things to be spread out than concentrated. Let me give you another example, a simpler one. Suppose I flip a coin 100 times. What's the most likely outcome? About 50 heads and 50 tails. Not exactly 50, but close. Why? Because there are enormously more ways to arrange 100 coin flips to get roughly 50 of each than to get, say, all heads or all tails. The probability of getting all heads is 1 in 2 to the 100th power. That's about 1 in a trillion, trillion, trillion. It'll never happen. But the probability of getting something close to 50-50 is high because there are so many different arrangements that give you that result. This is entropy. The 50-50 state has high entropy because it has many microstates. The all-head state has low entropy because there's only one way to achieve it. Now, let's go back to that cup of coffee. The hot coffee is a low entropy state. Not low in absolute terms, but low relative to the coffee plus surrounding air system. The energy is concentrated in the coffee. There are relatively few ways to arrange the molecular motions to keep all that energy in one place. As the coffee cools, energy spreads into the surrounding air. The molecules of the coffee slow down, the molecules of the air speed up a little, and the energy gets distributed more evenly. There are vastly more ways to arrange this spread out energy than the concentrated energy. So that's where the system goes, and it doesn't go back. Not because it can't, but because the odds against it are literally astronomical. Now, here's where it gets personal. Here's where it gets into your bones, quite literally. You are a very low entropy structure. Think about your body. Billions of cells, each one containing thousands of different proteins, each protein folded into exactly the right shape, each molecule in exactly the right place doing exactly the right job. The organization is staggering. Compare that to a cloud of gas, where the molecules are just wandering around randomly, or to a pile of ash, where the atoms are all jumbled up with no particular arrangement. You are spectacularly ordered. You are an island of low entropy in a sea of high entropy. How is this possible? Doesn't the second law say entropy always increases? How can you exist? This is where Schrödinger comes in. Erwin Schrödinger, the quantum mechanics fellow with the famous cat. In 1944, he wrote a little book called What is Life? And he asked this very question. His answer was beautiful. He said that living things maintain their low entropy by feeding on negative entropy from the environment. Or more precisely, they take in low entropy energy and excrete high entropy waste. Think about what you eat. Food is highly organized. Sugars, proteins, fats. These are complex molecules with specific structures. Low entropy. You eat this food, you break it down, you extract energy, and you excrete waste. Carbon dioxide, water, heat, all high entropy stuff. You're not creating order out of nothing. You're taking in order from outside and exporting disorder. The total entropy of you plus your environment goes up, just as the second law demands. But you manage to stay organized by constantly dumping entropy into your surroundings. And where does the low entropy in your food come from? From plants. And where do plants get it? From sunlight. Ah, now we're getting somewhere. The sun, our star, the source of almost all the order on Earth. The sun sends us photons, light, energy. But here's the crucial point. The sun doesn't just send us energy. It sends us low entropy energy. The photons from the sun are high energy, short wavelength, visible in ultraviolet light. They come from a source at about 6,000 degrees. And what does the Earth do? It absorbs this sunlight, uses some of it, and then radiates energy back into space. But it radiates at a much lower temperature, around 255 Kelvin. That means it radiates infrared photons, longer wavelength, lower energy per photon. Now, the total energy coming in roughly equals the total energy going out. The Earth is in approximate energy balance, but the entropy is not in balance. Low entropy light comes in. High entropy light goes out. The Earth is a conduit for turning low entropy into high entropy, and in the process, all the machinery of life can operate. Green plants capture that low entropy sunlight and use it to build complex molecules like glucose. Animals eat the plants, other animals eat those animals, and at every step, order is maintained locally while disorder is exported to the environment. You are part of this flow. You are a temporary eddy in the river of entropy, a local decrease bought and paid for by a much larger increase somewhere else. And here's the cold reality. This can't go on forever. The sun will burn out. The river of low entropy energy will stop flowing. And when it does, the game is over. But let's not get ahead of ourselves. Let's go back to the physics. I want to address a misconception head on. You've probably heard people say entropy means disorder. And there's truth to that. But it's a dangerous simplification. Consider this example. Take a bottle of Italian salad dressing. You know the kind, where the oil and vinegar separate into layers. That looks pretty orderly, right? 2 neat layers, oil on top, vinegar on bottom. Now shake it up. You get a cloudy mixture, all jumbled together. That looks more disorderly, doesn't it? But here's the thing. The separated state actually has higher entropy than the mixed state in many cases. Why? Because when the oil and vinegar are separate, each molecule has more room to move around in its own phase. The number of microstates can actually be larger. Or consider a crystal. Take salt, sodium chloride. The atoms are arranged in a perfect, regular lattice. It looks very orderly. But dissolve that salt in water, and the sodium and chloride ions are swimming around freely, all jumbled up. More disordered, right? Yet the dissolved state has higher entropy. Dissolving is spontaneous because entropy increases. The ions have more freedom of motion when dissolved than when locked in a crystal. So disorder is a rough guide, but it's not the full story. The real story is always about microstates. How many arrangements are possible? That's what determines entropy. Now let me tell you about the arrow of time. This is one of the deepest problems in physics, and entropy is at the heart of it. We experience time as flowing in one direction. The past is fixed, the future is open. We remember yesterday, but not tomorrow. Causes precede effects. This asymmetry is built into our very consciousness. But look at the fundamental laws of physics, Newton's laws, Maxwell's equations, Schrödinger's equation, the equations of quantum field theory. They are all time symmetric. Run them forward, run them backward, they work just as well. There's nothing in the equations that picks out a direction of time. So where does the arrow come from? The answer is entropy. The arrow of time is the direction in which entropy increases. That's it. That's the whole story. But wait, you might say. If the underlying laws are time-symmetric, why does entropy increase to the future and not to the past? This is a profound question. And the answer is not in the laws themselves, but in the boundary conditions, the initial conditions of the universe. Here's the key. The universe started in a state of extremely low entropy. The Big Bang, for all its violence and chaos, was actually a very special, very improbable state. The matter was almost perfectly uniformly distributed. There were no stars yet, no galaxies, no black holes, just a hot, smooth plasma. And from that special beginning, entropy has been increasing ever since. Stars form, burn, and die. Galaxies assemble and collide, black holes grow, and at every step, entropy rises. The arrow of time points away from the Big Bang because that's the low entropy direction. We remember the past because memory formation increases entropy. Causes precede effects because the cause-to-effect direction is the entropy increasing direction. So when you ask, why can't I unscramble an egg? The deep answer is because the universe began in a low entropy state, and the egg scrambling is part of the universal trend toward higher entropy. If somehow the universe had started in a high entropy state, a heat death state, nothing would happen. Nothing could happen. There would be no arrows of time, no processes, no life, no clocks, no memories, just equilibrium forever. Let me pause here and restate this idea as simply as I can. Imagine I'm explaining this to a bright 12-year-old. Entropy is about counting. How many ways can you arrange the little pieces to get the big picture you see? If there are lots of ways, entropy is high. If there are only a few ways, entropy is low. Nature goes from few-way states to many-way states, not because of any mysterious force, but because many-way states are more probable. That's why coffee cools, gases spread, and eggs scramble. That's why time has a direction. That's why you get older and never younger. Okay, now let me show you something that will blow your mind. I want to do a little thought experiment. Just use your imagination. Picture a room full of air. Normal room, normal air. The molecules are zipping around in all directions at all speeds. Maxwell figured out the distribution of speeds in the 1860s. Some molecules are slow, some are fast, most are somewhere in the middle. It's all very random, very high entropy. Now imagine, just imagine, that by some miracle, all the molecules happen to be moving toward the right side of the room. Not permanently, just at one instant. They're all heading right. What would happen? The air would rush to the right. A powerful wind would blow. Then the molecules would hit the right wall, bounce back, and the whole thing would equilibrate again. But for one moment, for one instant, there would be a wind created out of nothing. You could put a little windmill in there and generate electricity. You could get work out of the system without adding any energy. A perpetual motion machine of the second kind. Of course, this would require a fantastically improbable fluctuation. The odds of all those molecules lining up by chance are so small that it would never happen. Not in a billion years. Not in a Google years. But here's the spooky thing. It's not impossible. The laws of physics don't forbid it. It's just incredibly, overwhelmingly unlikely. And this gives you a new way to think about the second law. The second law doesn't say entropy must increase. It says entropy almost certainly will increase. There's a subtle difference there, and it matters. Now, let me talk about what all this means for the far future. The ultimate fate of the universe. If entropy keeps increasing, and there's no reason to think it won't, then the universe is heading toward a state of maximum entropy. A state where everything is spread out, everything is the same temperature, and nothing interesting can happen. This is called the heat death of the universe. Not death by heat, ironically, but death by the absence of heat gradients. Death by sameness, death by equilibrium. The stars will burn out. The last red dwarfs will flicker and fade trillions of years from now. Black holes will evaporate through Hawking radiation over unimaginably long time scales. something like 10 to the 100th years. And then all that will be left are scattered particles, diffuse radiation, getting colder and colder, more and more dilute forever. No energy gradients, no processes, no life, no thought, no time, in any meaningful sense, just equilibrium, maximum entropy. The universe will have finished its journey from the special low entropy beginning to the generic high entropy end. It's a cold prophecy, a chilling vision, but it's where the physics leads. Now, some people find this depressing. The idea that everything we know and love is just a temporary fluctuation on the way to oblivion. But I don't see it that way. Think about what it means for there to be an arrow of time. It means that things can happen, events can occur, stories can unfold. Without entropy increase, there would be no change. Without change, there would be no life, no thought, no love, no discovery. The very thing that dooms the universe in the end is the thing that makes it interesting now. The second law of thermodynamics is not your enemy. It's the engine of existence. It's the reason anything happens at all. Every morning when you wake up, you're riding the entropy gradient. The sun's low entropy light flows in, you use it to stay organized, you export disorder, and you live another day. Every breath, every thought, every heartbeat is paid for by entropy increase somewhere. Your life is a process of borrowing order from the universe and giving back disorder. And when you die, the debt is fully repaid. Your structure dissolves, your atoms scatter, your personal entropy increases dramatically and irreversibly. But here's the remarkable thing. In between birth and death, you have this window, this brief, precious window where you're organized enough to think, to feel, to wonder, to love. The universe made you. The flow of entropy sculpted you out of chaos, and it will eventually reclaim you. But right now, in this moment, you exist. And that's something. Let me talk about one more aspect of entropy that's often overlooked. The relationship between entropy and information. There's a deep connection discovered partly by Claude Shannon in the 1940s when he was developing information theory. Shannon realized that the uncertainty about a system, the amount of information you would need to specify its exact state, is mathematically identical to entropy. If I tell you a gas has high entropy, I'm telling you that it's in one of many possible microstates, but I don't know which one. There are lots of possibilities. If it has low entropy, there are fewer possibilities, less uncertainty about its state. This connects to the whole notion of measurement and observation. When you observe something, you reduce your uncertainty. You gain information. But there's a cost. The act of observation, if done irreversibly, must increase entropy somewhere. There's no free lunch. This is related to Maxwell's demon, a famous thought experiment. Imagine a tiny demon at a partition between two chambers of gas. The demon can see individual molecules and can open or close a little door. If a fast molecule approaches from the left, the demon opens the door and lets it through to the right. If a slow molecule approaches from the right, the demon lets it through to the left. Over time, the fast molecules accumulate on one side, the slow ones on the other. One chamber heats up, the other cools down. The demon has sorted the molecules and decreased entropy without doing any work, or has it? This puzzle tormented physicists for decades. The resolution, worked out by people like Leo Szilard, Rolf Landauer, and Charles Bennett, is that the demon must store information about each molecule it observes. And when that information is erased, entropy increases. You can't get something for nothing. The connection between entropy and information is profound. Some physicists think it's the deepest connection in all of physics. Information is physical. Erasing information generates heat. And entropy, at its root, is about what we know and don't know about a system. Let me tell you a story about Ludwig Boltzmann, because his life is intertwined with this subject in a way that's both inspiring and heartbreaking. Boltzmann was an Austrian physicist working in the late 19th century. He was a big man, robust, passionate about his work, and he had this incredible vision. At a time when many scientists didn't even believe atoms were real, Boltzmann was building a complete statistical theory of matter based on atoms. He fought battles, intellectual battles. There were prominent scientists, philosophers even, who attacked his work. They said atoms were just convenient fictions. They said you can't build physics on things you can't see. Ernst Mach, a famous philosopher of science, was particularly harsh. He would sit in the front row of Boltzmann's lectures and shake his head disapprovingly. Can you imagine? You've discovered something profound about the nature of reality, and people won't listen. They dismiss your work. They say it's not real physics. Boltzmann struggled with depression throughout his life. In 1906, while on vacation with his family in Italy, he took his own life. He was 62 years old. And on his tombstone in Vienna, they carved the equation, S equals K log W, his formula for entropy, the inscription that would become one of the most famous equations in physics, though he never lived to see its full vindication. Within a few years of Boltzmann's death, Einstein's work on Brownian motion provided direct evidence for atoms. The atomic theory that Boltzmann had championed was confirmed. His statistical mechanics became the foundation of modern physics, and that equation on his tombstone became one of the pillars of our understanding of nature. There's a lesson in this. Sometimes the people who see furthest are the most alone. Sometimes the truth takes time to be recognized, but the truth wins eventually. It always does. Nature doesn't care about our disputes. It just is what it is, and Boltzmann saw what it is. Now, let me go deeper into why irreversibility is so strange. Because I don't want you to leave here thinking this is all obvious or trivial. It's neither. Take any process you can think of: a ball rolling down a hill, a fire burning, ice melting, an egg breaking. All of these processes have a direction. They go one way and not the other. Now film one of these processes. Let's say the egg breaking. You drop the egg, it falls, it shatters on the floor, yolk and shell go everywhere. Now run the film backward. The yolk and shell leap off the floor, assemble into a perfect egg, and fly up into your hand. You instantly know the film is running backward. Why? Because eggs don't unbreak themselves. That's absurd. That never happens. But look at any individual collision in that process. Any single molecule of egg bouncing off a molecule of floor. That tiny collision looks perfectly fine in either direction. There's nothing in the laws of physics that says it can't run backward. So here's the puzzle. If every tiny part of the process is reversible, why is the whole process irreversible? And the answer, once again, is statistics. The number of arrangements. When the egg is intact, the molecules are arranged in a very specific way. There are relatively few configurations that count as a whole egg. When the egg is broken, the molecules can be scattered in an enormous number of ways. The yolk can be here or there. The shell fragments can be arranged in countless configurations. There are astronomically more microstates corresponding to a broken egg than to a whole egg. So the reverse process, all those scattered molecules just happening to come together into a perfect egg, would require an incredibly specific conspiracy of motions. Every molecule would have to be moving in exactly the right direction at exactly the right speed. The probability of this happening by chance is so small that it's essentially zero. Let me give you another way to think about this. Suppose you had a deck of cards in perfect order. Ace of spades, two of spades, three of spades, all the way through to the king of hearts. Perfect order. Now shuffle the deck. What do you get? Some random arrangement. What if you shuffle again? Another random arrangement. And again, another one. The deck never spontaneously returns to its original ordered state. Why? Because there's only one perfectly ordered arrangement out of the 52 factorial possible arrangements. That's about 8 times 10 to the 67th power. The odds of shuffling your way back to the original order are astronomically small. This is entropy in action. The ordered deck is low entropy. The shuffled deck is high entropy. And shuffling only ever takes you from low to high, never the other way. Now, someone might say, but wait, couldn't you unshuffle the deck? Couldn't you, with careful attention, put the cards back in order? Yes, you could, but that requires intelligence, effort, work. You have to look at each card figure out where it goes, and put it there. That's not a spontaneous process. That's you, a highly organized system, using energy to impose order. And when you do that, you increase entropy elsewhere. You burn calories, you generate heat, you export disorder to your environment. The total entropy still goes up. This is the crucial point. Local decreases in entropy are possible, but they always come at the cost of larger increases somewhere else. You can clean your room, but you'll use energy and export entropy. You can grow a crystal, but the surrounding fluid will become more disordered. You can create a baby, but the process of gestation and birth generates plenty of entropy. Life doesn't violate the second law. Life exploits the second law. Life is a strategy for creating local order by exporting global disorder. Let me talk about clocks for a moment, because clocks are intimately related to entropy. What is a clock? A clock is anything that changes in a regular, predictable way. The ticking of a grandfather clock, the oscillation of a quartz crystal, the vibration of atoms in an atomic clock. All of these are systems moving through states in a well-defined sequence. But here's the thing. Clock mechanisms only work in one direction. The pendulum swings, the gears turn, the hands move around the dial. If you ran the clock backward, if you somehow reversed all the motions, it would look bizarre. The clock would still tick, but it would be fighting against the normal operation. It would be like watching a film in reverse. And why is this? Because a clock is a thermodynamic device. It consumes energy, usually from a wound spring or a battery, and it dissipates that energy as heat through friction. It's an entropy-producing machine. The entropy it produces gives the clock its direction. The clock doesn't just measure time. In a sense, the clock creates a local arrow of time through its own entropy production. This is subtle but important. The arrow of time isn't just out there in the universe. It's in every process, every system, every clock. And it's all connected. All the little arrows point the same way because they're all part of the same cosmic entropy gradient flowing from the Big Bang toward the heat death. Let me return to the cosmic picture for a moment, because I want you to appreciate just how strange the initial conditions of our universe were. Think about what the Big Bang was like. Shortly after the beginning, the universe was a hot, dense soup of particles. Protons, neutrons, electrons, photons, all bouncing around at tremendous energies, and the matter was distributed almost perfectly uniformly. The density variations were tiny parts per 100,000. Now, you might think a uniform distribution is high entropy. After all, isn't uniformity a kind of disorder? Everything the same everywhere? But wait, we said earlier that entropy is about counting microstates. And here's where gravity changes everything. For ordinary matter without gravity, a uniform distribution is indeed the maximum entropy state. The gas in a box spreads out evenly. That's equilibrium. That's high entropy. But when gravity is important, things are different. Gravity pulls matter together. A smooth distribution of matter under gravity is actually unstable. It will clump. Small density variations will grow. Matter will collect into stars, galaxies, clusters. So for a gravitating system, the uniform state is low entropy and the clumped state is high entropy. Counterintuitive, but true. Maximum entropy for a gravitating universe is not a smooth distribution, but a universe full of black holes. Black holes are the ultimate entropy sinks. They're where entropy goes to die, so to speak. This means the early universe, with its nearly perfect uniformity, was in an extraordinarily low entropy state for a gravitating system. The Big Bang was special, improbable, very far from equilibrium. And as the universe evolves, entropy increases by matter clumping. Stars form, planets form, galaxies form. Gravitational potential energy is converted to kinetic energy, then to heat, then radiated away. Entropy rises and rises. Roger Penrose, the mathematical physicist, has estimated just how special the initial state was. He calculates that the odds of getting a universe like ours by chance, just from random initial conditions, are something like 1 in 10 to the power of 10 to the 123rd. a number so vast it makes the number of atoms in the observable universe look like a rounding error. Why was the universe so special? Nobody knows. It's one of the deepest mysteries in physics. Some people invoke the anthropic principle. Maybe only universes with low initial entropy can produce observers. So, of course, we find ourselves in such a universe. Others look to speculative ideas about cosmic inflation, about what happened before the Big Bang, about multiverses. But whatever the explanation, the fact remains. The universe started special, and it's been getting less special ever since. That's the cosmic arrow of time. That's why you're getting older instead of younger. That's why coffee cools and memories fade and stars burn out. Now let me talk about something practical, about how entropy shows up in everyday life in ways you might not expect. Think about your car. You put gasoline in the tank. That gasoline is a low entropy fuel. The molecules are hydrocarbons, complex chains of carbon and hydrogen with chemical potential energy stored in the bonds. When you burn the gasoline in the engine, you break those bonds, you release energy. That energy does work, pushing the pistons, turning the wheels. But not all of it. A lot of it becomes heat. The engine gets hot. The exhaust is hot. Heat dissipates into the environment. And what comes out the tailpipe? Carbon dioxide and water. Simple molecules. High entropy compared to the gasoline. The combustion process has taken low entropy fuel and converted it to high entropy exhaust, plus some useful work. The efficiency of your engine, the fraction of energy that actually moves the car versus the fraction wasted as heat, is limited by the second law of thermodynamics. There's a maximum efficiency called the Carnot efficiency, and no real engine can exceed it. The entropy tax is built into the physics. Or think about your refrigerator. The refrigerator does a remarkable thing. It takes heat from a cold place, the inside of the fridge, and moves it to a hot place, the kitchen. Heat flowing from cold to hot. That seems like a violation of the natural order, right? Heat is supposed to flow from hot to cold, but it's not free. The refrigerator uses electricity. The compressor does work. And for every bit of heat removed from the inside, more than that much heat is dumped into the kitchen. The total entropy still increases. You're just paying the entropy tax in a different currency. Power plants work the same way. They take heat from a hot source, a burning fuel or a nuclear reactor, and transfer some of it to a cold sink, usually the environment. The difference does work, generates electricity, but the efficiency is limited. The colder the sink and the hotter the source, the more efficient you can be. But you can never be perfectly efficient. There's always waste heat. Always entropy production. This is why perpetual motion machines don't work. Not because engineers aren't clever enough, but because the laws of thermodynamics forbid it. You cannot create a machine that runs forever without any energy input. You cannot create a machine that is 100% efficient. The entropy tax must be paid. Now, let me address another misconception. People sometimes think entropy means chaos or randomness in the sense of unpredictability. But that's not quite right either. Consider a perfect crystal at absolute zero temperature. This is the lowest entropy state possible for a physical system. The atoms are locked in place in a perfect lattice. No motion, no uncertainty. The entropy is exactly zero. Is that chaotic? No! It's the opposite of chaotic. It's completely ordered and completely predictable. And consider a gas at high temperature, molecules zooming everywhere, high entropy. Is that unpredictable? Well, yes and no. The motion of any individual molecule is chaotic and unpredictable. But the average behavior, the pressure and temperature, is completely predictable. That's the beauty of statistical mechanics. Individual randomness gives rise to collective regularity. So entropy isn't about predictability exactly. It's about the number of possible arrangements. It's about how much information you would need to specify the exact state. A high entropy state is one that could be any of many possibilities. A low entropy state is one that must be one of few possibilities. This is why the word information keeps coming up. Shannon entropy and thermodynamic entropy are deeply connected. When you learn something, when you gain information about a system, you're effectively narrowing down which microstate it's in. You're reducing your uncertainty, and that has thermodynamic consequences. Now, let me address aging more directly, because that's what the title promised, right? What entropy is doing to you right now. Your body is a machine, an incredibly complex, self-repairing, self-regulating machine, but it's a machine nonetheless, and it runs on thermodynamic principles. Every cell in your body maintains a state far from equilibrium. The concentrations of sodium and potassium ions inside and outside your cells are carefully regulated. The pH is controlled. The temperature is constant. All of this requires energy, and all of this generates entropy. Let me give you a concrete example. Your heart. It beats about once a second, roughly 100,000 times a day, 37 million times a year. Each beat is a coordinated contraction of muscle cells, requiring calcium ions to flow in, proteins to slide past each other, ATP to be consumed, and after each beat, the system must reset. Calcium must be pumped back out. ATP must be regenerated. It's an astonishing feat of biological engineering. But every one of those beats produces entropy. Heat is generated, molecular wear and tear accumulates, the machinery doesn't run perfectly, small errors creep in. Over decades, those errors add up. The same is true everywhere in your body. Your DNA is constantly being damaged by radiation, by oxidation, by random chemical insults. And your cells are constantly repairing that damage. But the repair isn't perfect. Some damage gets through. Mutations accumulate. Cellular function degrades. Your proteins are constantly being damaged and replaced. But the replacement isn't perfect either. Sometimes the new proteins misfold. Sometimes the wrong proteins are made. Sometimes the cellular machinery that makes proteins makes mistakes. All of this is entropy in action, the continuous effort to maintain order against the relentless tide of disorder. There's a beautiful concept in physics called the fluctuation dissipation theorem. It says that any system in contact with a heat bath will experience random fluctuations. The hotter the bath, the larger the fluctuations. These fluctuations are the microscopic manifestation of thermal energy, of entropy. Your cells are in a heat bath. Your body temperature is about 37 degrees Celsius. That's warm enough for rapid chemistry, for life processes to happen at a good clip. But it's also warm enough for random thermal fluctuations to occasionally knock things out of place, to damage a molecule here, misplace a bond there. Life is a constant battle against these fluctuations. Your cellular machinery is exquisitely designed to resist them, to repair damage, to maintain order. But no defense is perfect. Over time, the fluctuations win, entropy increases, you age. Some researchers have actually calculated the entropy production in human bodies over a lifetime. The numbers are staggering. Over a typical human lifespan, your body generates thousands of kilojoules of entropy per kilogram of body mass. That entropy gets exported to your environment as waste heat, as exhaled gases, as all the entropy of living. And there seems to be a limit, a maximum lifetime entropy generation that bodies can sustain before the damage becomes overwhelming. Cross that threshold, and the systems start to fail. Organs degrade, diseases take hold, death approaches. This doesn't mean aging is simple or that we can't do anything about it. Biology is complicated. Diet matters. Exercise matters. Medicine matters. But at the deepest level, your mortality is a thermodynamic fact. Let me do another thought experiment. Suppose I could somehow show you a movie of your own molecules over the course of a year. You'd see atoms coming in, food you ate, air you breathed. You'd see atoms going out, exhaled carbon dioxide, water vapor, waste. You'd see molecules being built and broken down, proteins synthesized and degraded, DNA replicated and repaired. Now imagine running that movie backward. You'd see atoms going in that should come out, carbon dioxide being inhaled and turned into glucose, waste products becoming food. You'd see muscles growing stronger as you lift weights, and the weights lifting you everything backward. That backward movie would look absurd, impossible, miraculous. Why? Because every single process in your body increases entropy. Running them backward would decrease entropy. And that doesn't happen spontaneously. Your life is a thermodynamic process. It has a direction because entropy has a direction. You are time's creature, shaped by the arrow, carried by the current. Now I want to talk about the far future again, but in more detail, because the time scales are mind-boggling, and I want you to appreciate them. Right now, stars are burning. Galaxies are shining. The universe is active and interesting. Entropy is increasing, but there's still plenty of room for it to increase more. In about 5 billion years, our sun will exhaust its hydrogen fuel. It will swell into a red giant, possibly engulfing Earth, then collapse into a white dwarf, a slowly cooling ember the size of Earth, but with the mass of the sun. In about 1 trillion years, the last stars will have burned out. No more nuclear fusion anywhere. The universe will be dark, only black holes, neutron stars, white dwarfs, and scattered debris. In about 10 to the 40th years, even the protons in ordinary matter might decay. This is speculative. We don't know for sure if protons decay, but some theories suggest they might. If they do, ordinary matter will dissolve into radiation over unimaginably long timescales. In about 10 to the 100th years, the last black holes will evaporate through Hawking radiation. Stephen Hawking showed in the 1970s that black holes aren't perfectly black. They emit radiation very slowly and gradually shrink. A stellar mass black hole would take longer than the current age of the universe to evaporate. A supermassive black hole would take far longer, but eventually, given enough time, even they go. And then what's left? A thin soup of photons and leptons, spread out across an exponentially expanding space. The temperature approaches, but never quite reaches absolute zero. Nothing happens because nothing can happen. No energy gradients, no processes, no change, maximum entropy. Heat death. The end of time in any meaningful sense. Now, some physicists have speculated about what might happen after that. Could quantum fluctuations create new structures? Could the vacuum decay to a new state? Could a new Big Bang somehow emerge? We don't know. Our theories become very speculative at these extremes. But the basic picture is clear. The universe is running down. It started wound up, special low entropy, and it's unwinding, becoming generic high entropy. We are living in the interesting part, the part where things happen, and that part is finite. Let me come back to the question of why the universe started in such a low entropy state. This is called the past hypothesis, and it's one of the deepest problems in physics. David Albert, a philosopher of physics, calls it the most interesting problem there is. Sean Carroll, a cosmologist, has written extensively about it. Penrose has called it the biggest puzzle in physics. Here's the issue. The laws of physics, as we understand them, are time-symmetric. They don't prefer one direction of time over another. So you can ask, why does entropy increase toward the future? And the answer is that the universe started in a low entropy state. But then you can ask, why did the universe start in a low entropy state? The laws don't explain that. It's a brute fact, an initial condition. And that feels unsatisfying to many physicists. Some have proposed that there's a deeper law, a law about initial conditions, that explains why the universe started as it did. Others invoke the anthropic principle. Only universes with low initial entropy can produce observers, so we necessarily find ourselves in such a universe. Still others, like Carroll, have proposed that perhaps our Big Bang is just one event in a much larger multiverse where different regions have different entropy histories. Maybe entropy is low in our past because entropy was high in some other region's past, and our Big Bang was a fluctuation. These are speculative ideas. We don't know the answer. But the question itself is profound. Why is there an arrow of time? Why does entropy increase? These are not silly questions. They go to the heart of what it means to exist in a universe with before and after, with cause and effect, with birth and death. Let me tell you about one more thing. The connection between entropy and the geometry of space. This might seem like a strange topic, but it's one of the most exciting areas of modern physics. It turns out that entropy and space-time are deeply connected. When Jacob Bekenstein and Stephen Hawking studied black holes in the 1970s, they discovered something remarkable. A black hole has entropy, and the entropy is proportional to the area of its event horizon, not its volume. This is strange. For ordinary systems, entropy scales with volume. More stuff, more microstates, more entropy. But for black holes, entropy scales with surface area. This led to the holographic principle, the idea that the maximum entropy in any region of space is proportional to the surrounding surface area, not the interior volume. It's as if all the information about what's inside is encoded on the boundary, like a hologram. Some physicists think this hints at something deep. Maybe space-time itself emerges from more fundamental ingredients, and entropy is the thread that connects them. Maybe the reason for the arrow of time is written into the structure of space itself. This is very speculative, at the frontier of physics, but it shows that entropy is not just a practical concept for engineers worrying about steam engines. It's connected to the deepest questions about reality. What is space? What is time? Why do we exist? You came in here asking what entropy is doing to you right now, and I've tried to answer that question. Entropy is aging you. Entropy is running down your battery, wearing out your parts, pushing you toward equilibrium. But entropy is also making you possible. Without the flow of entropy from the sun, without the entropy gradient from Big Bang to heat death, there would be no life, no thought, no you. You are a temporary victory against the tide, a brief candle in the cosmic dark, and the very thing that will snuff you out is the thing that lit you in the first place. Now, I want to end with something that I find deeply beautiful about all of this. The universe didn't have to start in a low entropy state. As far as we know, there's no reason it had to. The Big Bang could have been high entropy from the start, and then nothing would ever have happened. No stars, no planets, no life, no us. But somehow, for reasons we don't fully understand, the universe began in a state of extraordinary specialness, an improbable state, a state with enormous potential for entropy to increase. And as that potential gets realized, as entropy flows uphill through the vast reaches of time, all the complexity we see emerges. Stars ignite, planets form, chemistry becomes biochemistry, life arises, intelligence evolves. Beings like you and me sit in rooms like this and wonder about entropy. We are entropy's children. We exist because the universe had entropy to spare. We are the temporary eddies, the local decreases, the brief borrowings of order that the second law allows. And we won't last forever. Nothing does. But we're here now, and that's not nothing. That's everything. So the next time you feel the warmth leave your coffee, or you notice a gray hair in the mirror, or you watch the leaves fall from a tree in autumn, remember what you're seeing. You're seeing entropy. You're seeing the arrow of time. You're seeing the universe doing what it does, flowing from less probable to more probable, from special to generic, from order to disorder. And remember that you're part of that flow. You're not separate from it. You're a feature of it. A particularly interesting feature, I'd say. A feature that can understand what's happening to it. That's the privilege and the tragedy of being human. We know we're mortal. We know entropy will win. But we also know that right now, in this moment, we're the universe looking at itself and marveling at the view. And that, my friends, is what entropy is doing to you right now. Now, I want to hear from you. Here's a question to think about, and I'd love to know your answer. If you could somehow watch the heat death of the universe and then come back, what do you think it would look like? Complete emptiness? Or maybe something we can't imagine? Leave your thoughts in the comments below.